Hi there, everybody. In this lecture, I'm going to talk to you about brainstem reflexes. Try not to get discouraged. They are a little bit complicated and they take a little bit of thinking through to get a good understanding. Every time I teach this, I have to sit and kind of go through this again to make sure that I understand it. But what it ends up doing is helping you have a better feel for how the brain talks to the brainstem and why we do all these tests to try to localize where the problem is. So the objectives are to discuss how the vestibulo-ocular reflex works, to describe the process of using cold and warm caloric testing, and to differentiate between optokinetic and rotatory nystagmus. So the vestibulo-ocular reflex is a primarily brainstem reflex. So this is super helpful because it doesn't require any cortical input. And using the vestibulo-ocular reflex allows you to check how the mechanisms of the brainstem are working. And how to do this is to actually just have your patient, if they're alert and awake, look at something and move their head back and forth. The vestibulo-ocular reflex is what keeps your eyes focused on whatever you're looking at despite of where you're turning your head. So it can be in the horizontal plane and it can be in the vertical plane. If your patient is unconscious, you can also use the vestibulo-ocular reflex. The patient, if they're unconscious, will often keep their eyes steady. So this reflex is often called the doll's eye reflex, and this is not a doll with painted on eyes. This is a doll with those creepy eyes that follow you around the room. They're the ones that are weighted. So the idea is that the eyes always stay in one place no matter where the head is, okay? So what happens in the vestibulo-ocular reflex? So this is primarily a reflex that involves the vestibular system, in particular the horizontal semicircular ducts in the inner ear. And so what happens is when you turn your head, input comes from the vestibular system via the vestibular ganglion and then to the vestibular nuclei. And then the vestibular nuclei actually talked to the sixth cranial nerve to activate the gaze to move to the right to compensate for the head rotation, and back to the left, so that it always stays front. Does that make sense? The idea is that the rotation occurs, like the head turns this way, and then you activate the eyes to keep them here. And this is like spontaneous. Like this is an amazing process because it happens like instantaneously. So one more time. So what this is showing is that there's rotation of the head to the right and to the left, which makes the eyes, you want to activate the gaze to move the eyes to the right. So you turn the head to the left, the cranial nerve 6 moves the lateral rectus over, and cranial nerve 3 moves the medial rectus over, and they stay looking straight ahead. Okay? And then if you change to the other side, it activates the other PPRF in cranial nerve 6 nucleus and brings things over to that direction. It's really quite amazing. And like I said, remember, this is a brainstem function. So from here, everything else that we're going to talk about involves the cortical control and how we are able to tell whether or not a lesion is cortical or brainstem mediated. And so as you'll remember, we talked about saccades and smooth pursuit. And saccades in particular are generated from the frontal eye fields, and the smooth pursuit is from the striate cortex. The striate cortex, remember, is involuntary, and that's more responsible for just following whatever object your brain's interested in looking at. The frontal eye fields is voluntary. That's how you tell your eyes, hey, I want to look over there, and now I want to look over there. And so that is very volitional and very frontal lobe. So that makes it a little bit easier to remember where these are coming from. So caloric testing is a test of the brainstem function, but also turns out a test of the frontal eye fields. So vestibulo-ocular nystagmus is produced when you instill cold or warm water into one ear. And cold and warm cause different reactions. And I'll show you a picture in a second. So what happens is that there is a driving of the eyes in a certain direction based on the vestibular ocular system. But then, because the frontal eye fields are when the frontal eye fields are functioning, there's a rebound saccade that tries to move the eyes back to center. The stimulus from the ear actually will generate an initial slow phase, and then the fast phase is compensatory, right? So this heating or cooling produces opposite convection currents and activates the semicircular canals and causes the responses that we see. And the mnemonic that we use for this is cold, opposite, warm, same. And that represents the nystagmus quick phase. This is absolutely essential. So as I'll show you in a second, if you instill cold water into the right ear, it will drive the eyes over to the right ear slowly, but then the quick phase is in the opposite direction, right? So it's, hey, why are you putting cold water in my ear? And then the nystagmus goes in the opposite direction. If there's warm water goes into the right ear, it drives the eyes away, and then the quick phase is in the direction that's being stimulated with the water. And here's a diagram showing this. So in a normal patient, if you're instilling cold water into the right ear, the eyes are driven slowly, that's what the S stands for, slowly over to the right, and then there's a fast phase that moves in the opposite direction. If it's warm water being instilled, the eyes are driven away slowly from the stimulus, but then there's a fast phase nystagmus back towards the stimulus. So cold, opposite, warm, same. Now, the next step is knowing what all of this means. So if the brainstem is intact, but the frontal eye fields are not functioning, then you don't have the compensatory saccade. And in that case, all you have is this slow tonic deviation of eyes, either toward the stimulus or away from the stimulus, depending on the temperature. If there's a lesion within the brainstem, such as a lesion of the medial longitudinal fasciculus in both eyes, that instead of both eyes being driven over, only one will be driven over, but because the MLF isn't working, and the MLF sends information from the PPRF to the cranial nerve 6 nucleus and then up across to the third nerve nucleus, you don't get the adduction, right? And you'll remember back to the internuclear ophthalmoplegia, if you have a lesion of adduction, that's caused by an ipsilateral MLF lesion. So if it's, and this is showing someone with bilateral MLF, but the problem here, so if you put cold water in and drives the eyes to the right, the left eye will not go because there is no information getting to the medial rectus nucleus. Same thing in the other eye. So if it's a bilateral lesion, then they will, the portion, the signal going to the lateral rectus is fine, but the signal going to the opposite medial rectus is dysfunctional. So they will have only the slow phase of slow movement of one of their eyes. If there is a lesion lower in the brainstem affecting the horizontal eye pathways, in particular the PPRF and the cranial nerve 6 nucleus, then there will be no movement because there is no information from the vestibular nuclei getting to the horizontal eye movement pathways. So there will be no movement in either direction. Okay? So our next slide is to talk about optokinetic nystagmus. And this is an amazing phenomenon. And what it is it's a cortical phenomenon. And this is how we are able to function in the world. You'll see this all the time. If you're ever sitting on an L and you happen to look at the person, and you're coming into a station, you happen to look at the person across from you, what you'll see is their eyes will kind of move slowly in one direction and have a quick saccade and going back. You can also see this if you're watching someone watch a train go by, watching traffic go by. How we kind of bring this on in everyday life or in our practice is to use what we call an OKN tape or an OKN drum. And so what this is, it's a little piece of fabric that has stripes, and it simulates a situation where you have to try to process information that's moving quickly. And so what you want to do when something's going quickly, you want to keep your macula directly on whatever you're looking at. But at some point, if you're following something, you've got to bring it back to continue to process information. So what optokinetic nystagmus is a slow phase in the direction of the stimulus with a fast phase back. Okay? And I'm going to show you a video of OKN. And this is a tape, and so this is in the vertical direction. So you can see a slow phase moving up and then down, and then up with a downward saccade, and then down with an upward saccade. And let me show that one more time. So again, this is with the tape moving up, the eyes move up slowly and down fast. It's hard to appreciate, but sometimes, honestly, it's easier to see the saccades than it is the slow movement. So I'm going to show you just one more time. And let's just look at the quick movement. So with the tape going up, there is a fast down movement. And with tape going down, there's a fast up movement. And so that's exactly what happens in the horizontal plane as well. So if it's moving right, there's a quick left movement. And if it's moving left, there's a quick right movement. And it's a catch-up saccade. So I'm going to go back to the previous slide really quick. So in this case, there's a strip that's moving this way. This arrow represents the slow movement, and this one represents the fast. So the slow is mediated by the occipital lobe, like we talked about, the striate cortex that's modulating, causing that smooth pursuit. And then the saccade is the frontal eye fields going like, wait, we got to see more. So smooth pursuit, occipital lobe, frontal eye field, saccade. Smooth pursuit, saccade. So the OKN is basically a normal physiologic nystagmus that allows us to, that we use on a regular basis, but what we use it for in clinic is to make sure that both the occipital lobe and the frontal eye fields are both functioning. And obviously we're also checking brainstem function, because if the information isn't getting to the brainstem, then you're not going to have OKN nystagmus. The last one is a little complicated, so we're just going to kind of take this really slowly. And this is another physiologic nystagmus. It's rotatory nystagmus. And what we're doing with this is kind of using the vestibular nuclei and the frontal eye fields and the occipital cortex to processing information in the setting of your eyes moving, as your head moving quickly. So what we're seeing here is a head that's turning to the right. And when you first start accelerating to the right, the endolymph within the ear, within the cupula of the right ear, begins to kind of stimulate the vestibular nucleus. And in that situation, you are generating a smooth pursuit to try to keep your eyes looking forward. Then your frontal eye fields kick in and start to mediate a saccade in the opposite direction, because it's trying to keep up, it's moving away from the eyes. You get the VOR going, and then the frontal eye fields make saccades to keep them straight. Now, once the endolymph catches up, then the occipital cortex takes over from the vestibular nucleus, and then you're basically doing OKN. Okay, so it's a VOR first, because you're stimulating the vestibular system. Then the OKN kicks in because the occipital cortex has taken over, but the frontal eye fields are still bringing the eyes over. And then when you stop, then the endolymph moves in the opposite direction, and you stimulate the left ear. So then you get what we call rebound nystagmus, because then your eyes want to be driven in the opposite direction by the VOR, and then your opposite frontal eye fields come into play. Okay, so this is just a very characteristic example of the interplay between the nuclei and the occipital cortex and the frontal eye fields, and in particular VOR and OKN. And you use all of these functions in order to navigate through a world in which you're moving your head at all times. And so these are all normal things. When they are abnormal is when you start being concerned about brainstem and cortical function. And based on where you find the abnormalities on your exam, that helps you to localize where the problem may be. So that's all I have on brainstem reflexes. Like I always say, please feel free to contact me if you have any questions, and I'm always happy to discuss in one of our lectures or at the eye fair. So I hope that you're enjoying your time learning about the eye and brain, and I look forward to seeing you.